Hi there, I'm Seth, and in this video I'm going to show you how to make R do your trigonometry homework. In a recent video I showed you how to make R do your algebra homework, and it's kind of a similar story. I'm not sure that R is necessarily the best tool for this job, but if you want to learn the language, if you want to become fluent in the language, then you should learn as many different applications of the language as possible. And I do actually use R to solve trigonometry problems sometimes. So let's get into it. Here's what I'm going to cover in this video. First, I'm going to talk a little bit about what trigonometry is all about, and then I'm going to talk about how to use R to solve some basic trigonometry problems without relying on any mnemonics like SOH-CAH-TOA or anything like that. Okay, so what is trigonometry? I'd argue trigonometry is all about how to use known properties of the unit circle to solve problems relating to triangles and circles. This is the unit circle. Notice that its center is the origin of a Cartesian plane or whatever you want to call it. The radius is 1. So the distance from the center of the circle to the perimeter is 1. It's kind of a straightforward concept in some ways. People like to show really scary looking versions of this, which I don't think is necessary, but it turns out this is just insanely useful. Some properties of the unit circle. First of all, the circumference is 2 pi. You probably remember the formula for the circumference of a circle is 2 pi r. So when the radius is 1, that simplifies to 2 pi. Something that follows from that is that if we go halfway around a unit circle, the distance is pi. In fact, you could think of that as one way of defining pi. It's half the circumference of a unit circle. We like to think of this as starting right here at the coordinates 1, 0. So traveling 1 along the x-axis and then 0 in vertical space, 0 on the y-axis. We like to think of it in terms of movement counterclockwise. And we break it into halves of pi. So we think of traveling, well, okay, so if you think it through, the entire way around is 2 pi. That means half of the way around is pi, and half of half would be pi divided by 2. This corresponds to a 90-degree angle. If we keep going another 90 degrees, we get to 180, and also pi, as I'd already mentioned. If we add another half pi, we come to 1.5 pi, or we often represent it as 3 pi divided by 2, same thing. This corresponds to traveling 270 degrees around the circle. And then finally 2 pi all the way around the perimeter, the circumference, that corresponds to 360 degrees. Now, the way we talk about distance traveled around the circle, we express this in terms of radians, which sounds scary, but all that means is a distance of 1 radius. This is really easy in the context of the unit circle because the radius is 1. So a radian is just a distance of 1. The length of this arc right here that's purple is 1. So here's 1 radian, 2 radians, 3 radians. It's not quite halfway because halfway would be pi radians or 3.14. We can continue on to 4 radians, 5 radians, 6 radians, and it's not quite there because the full way around is 2 pi, which is a bit over 6 radians. Now, the thing about radians is that they're actually the same as degrees. Angles and arcs are 2 different ways of expressing the exact same concept. So in the same way that 0 degrees Celsius is the same as 32 degrees Fahrenheit, 90 degrees is the same as pi divided by 2 in radians. It's the same thing. So one way to think about this is to think about the equivalence between however many radians out of pi, so however much distance we've traveled along this arc, out of pi, where pi would be half the distance around the circle. This is the same as however many degrees out of 180, because 180 would be halfway around the circle. Okay, so for example, right here, 90 out of 180 is the same as pi divided by 2 out of pi. They're both half the way around the circle. So we can rearrange this formula to do some useful things. Specifically, if we wanted to find, let's say we have degrees and we want to convert it to radians, we can just rearrange this formula. If we want to isolate the radians, you could multiply both sides of this equation by pi, and you get this equation. So the length in radians is equal to whatever your angle is, your degrees, times pi divided by 180. You could think of it as just having rearranged this straightforward equality, or you could kind of think of it as taking whatever proportion of 180. So here we have 90 degrees, so that's 90 out of 180, or 1/2, and multiplying it to find what proportion that is out of pi. So half of the way to pi is pi divided by 2. We can do the same thing the other way around. Suppose that you've got radians and you want to convert to degrees. We can rearrange this formula. We want to solve for degrees, so multiply both sides by 180, and we end up with, you take your radians, multiply by 180, and divide by pi, and that's going to spit out whatever the angle is in degrees. So angles and arcs are the same thing expressed two different ways. Okay, now in my opinion, trigonometry, basic trigonometry, boils down to these two concepts: cosine and sine. There's more fun stuff you can do, but ultimately, in my opinion, it all boils down to these two simple concepts. Specifically, when we've got a unit circle, we can take any radius, or really we can take any degree. So like 60 degrees, that means we've traveled this distance, which happens to be 1/3 of the way to pi. So another way to represent 60 degrees is as pi divided by 3, because 3 times 60 would be 180. We can take this and we can form a right triangle. You can do this for any degrees or any amount of radians along the unit circle. It's going to form a right triangle. This line, this horizontal line segment, which is the distance between whatever point we're at and the y-axis, we call that cosine. And the distance, the vertical distance between that point and the x-axis, we call sine. So these aren't constants. When you hear sine and cosine, those will change for every radian or for every degrees. They'd be different if we were looking at this point right here or this point over here. But cosine's always going to be the distance from the y-axis, and sine is going to be this line segment, which is the vertical distance from the x-axis. And it just so happens that for any number of radians or any amount of degrees within this unit circle, we happen to know what cosine is and what sine is. That may not sound particularly profound, but this is extremely useful. Now, to demonstrate what we're doing in trigonometry, I'm going to switch over to Desmos. All the other visuals and all the calculations in this video are done in R, but for this one demonstration, I just want to use Desmos because it is absolutely perfect for illustrating the concept of trigonometry, the core concept. Okay, so here we are in Desmos. You can see a lot of scary looking stuff happening over on the left side, but just completely ignore all of that. None of that really matters for what we're doing right now. I just want you to focus on this visualization in the center. So here's the situation. We know the length of this leg is 2, and we know that this angle right here is 60 degrees. And the question is, what is the length of this line segment, the smallest of the 3 legs of this triangle? Now, a lot of people would look at that and they would think, ooh, looks like a right triangle. If I had more information, like maybe if I knew the length of this leg, I could use the Pythagorean theorem or something like that. Well, trigonometry says no, we have exactly enough information to find out what the length of this leg is. And here's how it works. what trigonometry does in the way that I think about it is it takes our triangle and it scales it down to the dimension, to the size of a unit circle, or if it were smaller than a unit circle, it would scale up, but it scales the triangle to the size of a unit circle. And then, because as I told you earlier, we happen to know the length of this leg, this is called cosine in the unit circle, and we happen to know the length of this leg if it's in the unit circle, we can use that information to find what it would be if it were the full-size triangle. So I'll tell you how we can find those in a minute, but for right now, just accept the fact we're able to know what this length is in the unit circle. Okay, so let's find out. So using methods that I'll explain, we know that if this triangle were small enough to fit inside a unit circle, this leg would have a length of 0.5. So we found that, and now what we do is we scale the triangle back up to the original dimensions. And that tells us what the original length of this leg is. Now, this is the way I think about trigonometry. Not everybody thinks about it the same way, and I'm not going to say this is the right way or anything like that. But to me, this is a way where you can look at it and visually and intuitively understand what is going on, rather than simply memorizing some mnemonic like SOH-CAH-TOA. I don't want to get on a soapbox too much, but it seems to me like one of the main purposes of mnemonics is to help you avoid understanding what is actually going on. So to me, it's better to just actually understand. And if you do, you're not going to need any kind of mnemonic to remember. So what did we do? Let's walk through the logic. We have this is our original triangle. We know this length is 2. We know this angle is 60 degrees, and we're trying to find this length. We don't know what it is yet. We scale this down to the dimensions of a unit circle. We make the triangle fit inside a unit circle. Notice the radius here, this hypotenuse, is 2. So if we're going to scale it down to fit inside a unit circle, we have to divide the dimensions by 2. And so now it becomes 1, because that's a unit circle is defined as having a radius of 1. That means once we find what this line segment is, to get back to the original dimensions, we have to we have to multiply it by 2. We divided by 2 to get the dimensions down to fit inside a unit circle. Now we're going to have to double that value to get back to the original dimensions, and that's how we would find in the actual triangle the dimensions are 1. Or sorry, the dimension of this leg is 1. Okay, so while we're here, I'm going to briefly walk us around. Let me put it in the context of the unit circle again. I just want to walk this around a little bit so we can make sure we're really clear on what sine and cosine are. So you can see how the values of cosine and sine, which are these, this is cosine, that's the length of this segment. Sine is the length of this segment. You can see how it changes based on how many degrees we're at. So remember, we always kind of start right here at the coordinate 1, 0, where cosine is 1 and sine is 0. There's no vertical distance from the x-axis. And then we think of it as traveling counterclockwise. And you can see how sine and cosine are changing as we go around. And I'm just going to bring it to this angle because I frankly didn't feel like trying to figure out how to make it go all the way around for this visualization. But here, sine is now 1 and cosine is 0 because the vertical distance from the x-axis is 1, the horizontal distance from the x-axis is 0. So that's what we're doing. Now, I told you that we happen to know what cosine and sine are for every single triangle that we can form inside this unit circle. So let's talk about how we know that. Now, sometimes it's just going to be visually obvious. So like I gave you this example where this isn't even a triangle, it's just a flat line. So here, for 0 degrees, you don't need to do any calculations or anything. You should just be able to see cosine is 1 and sine is 0. Similarly here, cosine is 0 and sine is 1. So sometimes it will be just visually obvious. In other situations, we can use known properties of triangles to find the answer. So like in this example right here, this happens to be a 30, 60, 90 triangle, and maybe you just happen to know that in a 30, 60, 90 triangle, this short leg is half the length of the hypotenuse. What is the hypotenuse in a unit circle? Right here, this triangle, that's a distance of 1. So cosine has to be 0.5. So maybe you're just able to work it out based on principle or properties of triangles that you happen to know. Depending on what information you have available, you may be able to use the Pythagorean theorem. And if all else fails, for every other situation, you can approximate cosine and sine to a high degree of precision using something called a Taylor polynomial, which is kind of outside the scope of this, because the way we actually tend to calculate cosine and sine in practice is using calculators. I just want you to know there's ways that we can find it out, and the way we tend to do it is using a calculator. And that's what I'm going to talk about in terms of how we can use R. Here are the functions for what I consider to be the two main trigonometric functions, which are sine and cosine. Use sin for sine and cos for cosine. Now, importantly, the input, the arguments that you put inside the parentheses, they're going to need to be expressed in radians. That's how the code is written. What that means is, if I want to find cosine for 60 using R, I can't just say cos, open parentheses, 60, close parentheses. I've got to convert it to radians. And I showed you how to do that before. We can multiply the number of degrees times pi and divide by 180. So now the input is in radians, and we see that cosine of 60 degrees is 0.5, which we knew that's what it would be because we just solved that a minute ago based on the properties of 30, 60, 90 triangles. Similarly, for sine, we say sin, open parentheses, 60 degrees times pi over 180, that converts it to radians, and we find that it's about 0.87. That's the length of this line segment. Now, you can also use R to find the length of the tangent line. This is abbreviated as tan. So what we're talking about here, the way we often think about this is as the line that is perpendicular to the radius. It starts right here and it extends down until it hits the x-axis. So you can use this tan function if you want, but this happens to be equivalent to sine over cosine. The tangent line is equal to the ratio of sine to cosine. And I've kind of demonstrated that right here if you just want a demonstration of it. But this is also something that could be proved fairly easily. I guess maybe this would be one reason maybe to memorize SOH-CAH-TOA. The TOA means tangent equals opposite over adjacent. So the tangent is equal to the opposite line relative to this angle over the adjacent line to this angle. But to me, it's just confusing to try to then think of, okay, which is opposite? Does that mean sine or cosine? I don't see the value in that, especially because you can derive the fact that the tangent line is equal to sine over cosine in the moment, just from looking at this visualization. So I'm going to walk you through that very quickly. Notice how between the radius, the tangent line, and then the x-axis, there is this triangle formed. This is a right triangle, because remember, this radius and the tangent line, those are perpendicular. So this is a right triangle. The sine line, it's cutting this triangle into two similar triangles. When triangles are similar, that means the ratio of their sides is the same. So this small triangle is similar to this median triangle, and they are both similar to this large triangle. So let's think about what that would imply. That means the ratio of this medium leg to this small leg, in other words, the ratio of tan to 1 is the same as the ratio of this medium line to this small line in the small triangle. Medium to small, that ratio is the same as this medium to small in the smaller triangle. So the ratio of tan to 1 is the same as the ratio of sine to cosine. Anything over 1 is just itself, so you could re-express that as the tangent of a certain number of degrees is equal to sine over cosine for the same number of degrees. Now, I don't know how easy that is to work out in the moment. I don't know if I'm explaining that well, but to me, this is something you can just see when you look at the triangle, or you could study it a second and work out what it would have to be based on known properties of triangles. So I don't really see the value in memorizing something like SOH-CAH-TOA, but that's just me. Not everyone sees it the way I do. I just sort of remember from this, the tangent line has to be equal to sine over cosine. So I don't really use the tan function too much. I kind of just think sine over cosine if I needed that. Okay, now before we move on and start solving some problems, I also need to talk about the inverse trigonometric functions in R. What our standard functions do is they take arcs or angles as inputs, and then they output line segments. That's what we've been doing. We take like 60 degrees, and then cosine of that spits out 0.5 as a line segment. We can also reverse engineer that, taking in line segments and as our inputs and then outputting the corresponding arcs or angles. It's the same process, just in reverse, so these are called inverse functions. What we call these are, for cosine, it's called arc cosine. For sine, it's called arc sine, and for tangent, it's called arc tangent. So we abbreviate these as ACOS, ASIN, and ATAN. And what this does is, well, it just does the reverse. So we could input 0.5, we could input this length of cosine, and the function spits out the length of this arc, which is 1.05, just over 1 radian. This is the arc that corresponds to this value of cosine. Similarly, if we input 0.87 for arc sine, we're going to get the exact same arc, because that's the arc that corresponds to this value of sine. And similarly, if we put in arc tangent, a tan, for 1.73, which is this particular line segment, it's going to spit out the same 1.05 arc length, because in all three cases, this same arc corresponds to this value of cosine, this value of sine, and this value of the tangent. So that will be valuable. That will be useful for solving certain kinds of problems, as we'll see. Let's do it. So a person is standing at the edge of a building's shadow. They're standing right here. They're looking up to the roof. Okay, so they're looking up to the roof. The angle formed by their line of sight and the ground is 28 degrees. So this angle right here is 28 degrees. The building's 100 feet tall. So how far away is the person standing from the building to the nearest foot? Another way of asking this is, how long is this shadow? Okay, so let's think through what we've learned and how to apply these trigonometric concepts. First, we can scale this triangle down to fit inside a unit circle. Then we can see what factor we scaled down by. And then we can find cosine for 28, which will be this line segment in a unit circle, and we scale it back up to its original dimensions. Okay, so if that didn't make sense, I strongly recommend pausing and thinking through that logic real quick. We scale this triangle down to the size of a unit circle. We see what cosine for this segment is. So cosine for 28 degrees will give us this segment if it were scaled down to a unit circle. And then we scale it back up to the original dimensions. Okay, so first of all, we're going to scale this down to fit inside a unit circle. Okay, so let's get into R finally. I've forgotten what we're doing. Okay, so we're going to scale this down. To do this, we're going to find out what sine of 28 degrees would be. So we're going to find out what would this length be if we scaled this down to fit inside a unit circle. So sine of 28, remember we need radians as our input, so times pi divided by 180, and we get 0.469, so about 0.47. All right, sounds good. What that means is if we scaled this triangle down to fit inside a unit circle, that 100 feet would become 0.47 approximately. Okay, so we went from 100 down to 0.47. We need to see what factor we scaled down by. That's pretty easy to do. We can say 100 divided by, and I'm going to be very precise, by 0.46947, etc. This is equal to, I'm just going to call it 213. Because if we divide 100 by 0.469 and get 213, that means dividing 100 by 213 would also give us 0.469. So 213 is the factor by which we have scaled this triangle down. That also means that the length of this hypotenuse in the original triangle was 213 because we've divided everything by 213, so now this radius is just 1. All right, so there we go, 213. Here I am working that out. I rounded a little bit differently, but you can see it's still going to come out to approximately 213. Then the last step is, well, there's really two parts to this. We're going to find cosine of 28. So we're going to see what is this line segment inside the unit circle, and we know we've scaled down by 213, so we're now going to expand it out by a factor of 213. Okay, so we'll say cosine of 28 times pi, times pi divided by 180, and we could either find that and then multiply the result by 213, but I think we can just take two steps at once and say whatever that is, multiply that times 213. And the answer is 188.06, or to the nearest foot, 188 feet. Okay, so walking through those steps, so here I am finding cosine. I did it step by step originally when I made the slide. So cosine of 28 degrees is 0.88, and then we scale it up by multiplying that 0.88 times 213 to get approximately 188 feet. What that means is when we scale back up to the original triangle, the person is standing approximately 188 feet away from the building. Okay? Now, if we wanted to be fancy, we could solve it with a single line of code. And I'm just going to challenge you to pause the video and see if you can figure that out. What would be the single line of code which would give us all of this at once? There's actually many different ways that you could do this. Okay, I'm assuming you've taken the time to do it and now you're unpausing. Here's one way you could do it. I'm rounding to the nearest foot, so I'm using this round function. It's okay if you didn't do that. But ultimately, essentially, what we're doing is we're saying cosine of 28 degrees. We're scaling that up by a factor of 100 divided by sine of 28 degrees. So we're just taking our cosine and scaling it up by whatever that scaling factor is. That's what this line of code says. It's sort of like doing all those steps at once. Or you could algebraically rearrange this into an even simpler formula. So for example, this is probably how you're supposed to solve this. This can be algebraically rearranged into 100 divided by the tangent of 28 degrees. Personally, I don't find this very intuitive, so even though it's less code or maybe it's less steps, I don't really use computational formulas. I only use formulas that make sense to me where I could describe them. I use what are called definitional formulas where you can describe what's happening and it all makes sense for every step. So this isn't the way I would solve it because I don't find this particularly useful. I would solve it this way, but it does take more keystrokes or more steps potentially. So just know this might be what some people would expect you to do. But that's not how I'm going to solve it because I don't find that very intuitive. All right, let's do one more problem. This is actually going to be easier. And you know what? You're about to learn some real life knowledge. This is absolutely true. This will be useful for someone who needs to place ladders for your job. So to place a ladder safely, it's supposed to be positioned so that the angle formed by the ladder and the ground is 75 degrees approximately. Okay, so we have this 7-foot ladder and it is placed 3 feet from the wall. And we want to know, is this safely positioned? And we'll say anything between 78 and 80 degrees is approximately safe. Now, I hope that when you look at this ladder position, you have an intuitive sense of whether it's safe or not to step onto that. But let's use trigonometry in R to find out for sure. So this will be even easier. To solve this, we're going to scale this down to fit inside a unit circle. Doing so will also scale this length of 3 feet down by some amount. And then we're just going to use arc cosine to see what angle right here corresponds to whatever this line segment is after we've scaled it down. Someone's horn's going off. Hopefully you're not hearing that, but if you are, sorry. Okay, so 7 is 7 times longer than the radial line of a unit circle because, well, we're going to be dividing 7 by 7 in order to make it 1. That means we've got to scale 3 feet down by the same factor. You could do that in R or any way you want. It comes out to about 0.43. 3 divided by 7 is 0.43 approximately. And then we can simply use arc cosine to find the length of the arc in radians. For a cosine value of 0.43, we're asking, what is the length of this arc? Now, of course, what we care about is not the length of the arc. We want it expressed in degrees because the problem says we're looking for 75 degrees. So we're going to have to convert the arc to degrees. So think through, how would you do that? Okay, let's do it. So let's see, we've got 7 divided by 3, or sorry, 3 divided by 7, 0.428571, etc. Okay, we're going to use arc cosine for, you know what, I could type all that, but I'm just going to say 3 divided by 7 for simplicity. Oh, here I am. If you get a surprising result, that's a pretty good sign you've done something wrong. So I did not convert it from radians back to degrees yet. I was a little surprised. 1 degree, that's pretty surprising. So we're going to convert the result to what, an degrees. So that means we're going to need to multiply by 180 and divide by pi. Okay, and our result is 64.6, which I'm going to round to about 65 degrees. Okay, so this is not safely positioned. Remember, we said between 70 degrees and 80 degrees would be considered safe, so this ladder's not safely positioned. I hope that when you look at this, you would be afraid to step onto that ladder thinking, oh no, it's going to slide out from under you and you're going to fall. This is what a 75-degree angle would look like, which is approximately what a ladder should be positioned at. Okay, now again, we could solve this with a single line of code. Here we've got arc cosine of 3 divided by 7 times 180 over pi, and then we're just rounding to the nearest integer for just 65 degrees. Now, let's talk about a few other functions you might care about. Some other trigonometric functions are the reciprocals. So if you, for some reason, care about functions like arc cosecant, cosecant, arc cotangent, if those things are meaningful to you and you want to be able to calculate those using R, you could use something like the Pragma package, which has all of these fun little functions. I personally don't use that because these values, so secant of some value is the same, it's the reciprocal of 1 divided by cosine of that value. So I'm probably not going to download another package just to calculate what I could find by taking the reciprocal of an existing function, but that's just kind of how my mind works. I like to build things up from simpler things So I personally wouldn't use the package like that, but you could if you wanted to. There are packages out there for these purposes if you need to use that sort of thing. Additionally, and kind of the last thing is there's also some variations of the cosine, sine, and tangent functions that are scaled in units of pi. So if you want cosine scaled in units of pi, you can use COS pi. For sine, it's sine pi. For tangent, it's tan pi. So for example, let's just walk around the unit circle. Cosine pi of 0 is going to be 1 because we're right here. We've traveled 0 pi's. So cosine is 1. After we go 0.5, so half of the pi, cosine becomes 0. There's no distance from the y-axis. Travel a full pi, so all the way halfway around the circle. Now we should have -1, and that's what we get for cosine. Go another halfway around the circle, and we're back to 0, and another halfway. So cosine pi of 2 is 1 because we've gone all the way back around, or all the way around, and we're back to a cosine of 1. So you could see how that works. If we input COS pi over 1/3, we'd end up right here. Am I right? Am I thinking about this correctly? Let's just see. Cosine pi of 1/3, yeah, 0.5. Because what this is saying, sorry if this is too small to see, but zoom in. Now at the end of the video, I'm finally zooming in so you can see what I'm doing. We're saying cosine of 1/3 pi is 0.5 because 1/3 pi is 1/3 of the way to halfway. So in other words, 60 degrees, because 60 degrees is 1/3 of the way to 180. So if I personally don't use this, but you might have a use for this, and that's how you do it. Okay, so I think that's it. I think that's all that I have to say about trigonometry in R. If you want to know about anything like how do we plot sine and cosine, or maybe even tangent curves in R, I could show you how to do this kind of thing. Or if you want to know how to plot these fun little unit circles and the cosine and sine line segments, I could make a video showing you how to do that. But yeah, just let me know if that's something you want. Otherwise, I think that's it. Okay, trigonometry in R. There you go. Have fun.